All right, let's continue our discussion of graphs and digraphs. You'll get a strong sense of this adjacency list idea as we start looking at some actual code. Yeah, as usual, I want you to take a look at my C++ and Java code, which is available, and it uses this adjacency list idea. We do have to consider a variation on directed graphs, namely arc weighted digraphs. Okay, but this is exactly like the idea of edge-weighted graphs. Okay, for ordinary graphs, we generalized from ordinary graphs to edge-weighted graphs. So you recall that was simply a matter of assigning to each edge a positive number, right? Each edge has a positive number associated with it called its weight. And when we switch from graphs to digraphs, it's really the same idea. So each arc gets assigned a positive number, which we call the weight of the arc. Okay, and here we're going to very definitely want to think of these weights as reflecting some kind of distance. All right, even if it's distance in a rather abstract sense. Okay, there are plenty of times when digraphs are used in order to represent, like the vertices might represent physical places, and the arcs might represent ways of getting from one place to another place. And in that context, the weight really might mean distance in a really direct sense. But more often than not, the vertices represent something rather different, and the distance, when we say the weight of an arc, and we want to think of distance, it's really not in a real sense of distance. It's more abstract. Okay, so here's a picture of an arc-weighted digraph. Okay, I think it pretty much speaks for itself. There's an arc from D to B, and the weight of that arc is 7.5, and so forth. So just as we did with ordinary graphs, we can talk about finding shortest paths in this digraph. But of course, we want to restrict to directed paths. Okay? Shortest directed paths in a digraph. Or a arc-weighted digraph in this case. Okay. So, for example, we can see that there's a directed path that goes from G to C to E, and we can see that the length of that path is 4.4 plus 5.9, which equals 10.3, right? And that's because the weight of the arc from G to C is 4.4, and the weight of the arc from C to E is 5.9, together to 10.3, and maybe we should call that the weight of the path, but honestly, it's more customary to call that the length of the path. So, it's kind of silly, but there it is. Okay, and that path that I just mentioned, that in fact is the shortest path from G to E. When you're interested in finding shortest paths, and frankly in other contexts too, there's a very important question that comes up concerning digraphs, and that is, are there any closed directed paths in the digraph? Okay? If a graph is such that it does not have any directed closed paths, then we say it is a directed acyclic graph. Okay? And the acronym DAG is very commonly used for this, and people even pronounce that DAG, right? So a DAG is a directed acyclic graph. Acyclic means there are no directed cycles in the graph, right? No directed cycles. Okay? There are no directed closed paths. And here's an example. Okay? Try as you might, you are not going to find a directed cycle in that graph, right? You can certainly, if you take away the arrows and make them just ordinary edges, then you would have a graph that has a cycle in it, right? A to D, D to E, and E to A would constitute a cycle in an ordinary graph if those arcs are just ordinary edges, but they're not. They're directed, okay? So what I just described went from D to E, but that's using the arc in the wrong direction, okay? So I think you get it. I think you see it. There are no directed cycles in this graph. Therefore, it is a DAG in this digraph. This digraph is a DAG. There's a fundamental fact about DAGs that we're not going to attempt to prove, but it's the following. Anytime you have a DAG, it's always possible to order in some fashion the vertices, let's say lay them out from left to right, in such a way that all of the arcs move from left to right. Okay? So here is one possible way of redrawing the DAG that we just looked at. And as you notice, all of the arcs are now moving from left to right. When you've reordered the vertices in this way, if you like, when you've drawn the DAG in this way, it's said to have been topologically sorted, okay? I have no real conception of where that language comes from. I'm not particularly thrilled with it, but that's what it's called, okay? So there are quite a few real-world problems where topologically sorting a DAG is a useful thing to do. And there's an algorithm that we're going to discuss now called Kahn's algorithm, named after a person named Kahn, of course. And it's used for this purpose of topologically sorting a DAG. Okay? So let's begin by describing the algorithm as much as possible in plain English. After that, we'll look at some code that actually implements it. Okay, so here I'll describe how Kahn's algorithm works using pseudocode, where I lay things out, as you understand, basically to look like computer programming code, but I'm not rigorous about syntax, and I'm more interested in expressing ideas from person to person, namely me to you. All right, so now here are the precise steps in Kahn's algorithm that will topologically sort the vertices of a DAG. It's only going to take 2 slides to describe the steps of Kahn's algorithm. There's a nesting of 2 loops, and frankly, it's really kind of slick. So the truth is, we'll go through and say what these steps are, how this algorithm is structured, and then it's going to take some time to really think about it and really believe that it does what it says it does. Okay, so Kahn's algorithm begins with a list of vertices, of all the vertices. So V is going to be a list of all the vertices, and I stress that this is a list so that it's not just a set. We're interested in having the vertices occur in the list in some order, okay? But it has to be said that this is not a particular order. This is just some arbitrary order. Okay, so begin with a list of all the vertices in some arbitrary order. And then Well, we're also going to need two empty lists, two lists that we're going to start putting vertices into. Okay, and then the algorithm proceeds by means of a loop, and this loop is going to repeat until the list V is empty. Okay, each time through this loop, what we have to do is go through the list V and identify any vertices whose in degree is 0. In other words, no arcs coming into the vertex, right? So for each vertex whose in degree is 0, copy that vertex into the list S. And now we begin another loop. We're frankly nesting two loops. So this is the beginning of an inner loop inside this outer loop. Okay? So the inner loop gets repeated until the list S is empty. And here's what happens inside this inner loop. Okay? The first vertex in the list S is removed from S, and it's copied into, it's put into the list T. So it's transferred from the list S to the list T. Okay, now here's a subtle thing. That same vertex has to be removed from capital V, and it also has to be, all of the arcs leading out of that vertex have to be removed from the DAG. Okay? So basically, we're changing the DAG, we're changing this directed graph by removing one at a time a vertex. We're removing a vertex here, and we're also removing at the same time all of the arcs that lead out of that vertex. Okay? So as this Kahn's algorithm proceeds, the DAG is going to get smaller and smaller. And big surprise, that's it. Okay? We've described the entire algorithm. The DAG eventually disappears, but what you end up with is a list, capital T, that contains all of the vertices from the DAG. In other words, all the vertices that used to be in capital V are now inside capital T instead. And it's true that we wiped out all the information about the DAG, but we've ended up with the vertices sorted, topologically sorted, right? In other words, we've got the vertices in the order that we described when talking about topological sorting, okay? And you know, actually, if we had maintained a copy of the original DAG, then we would not lose the original DAG. So we could, you know, we could still have the original DAG by maintaining a copy of it, and now we also have the vertices sorted in the topological sorted order that we discussed earlier. Okay.